Okay, hello everyone. This is Anudh Mishra. I am an MBBS student at AIIMS Bhuvneshwar. Today I am going to discuss the chapter Classification of Elements and Periodicity in Properties with all of you. So, this chapter I will cover with the point of view of your JE main, which is going to come in January, right? Your January attempt. So, firstly, I'll give you a brief overview of the chapter, followed by some previous year questions which I have taken out from the same chapter, and we will solve it after doing the overview of the chapter. All right, so let us start. This chapter basically covers all the principle of classification of properties. Okay, so how do you classify? What properties do you use to uh, put an orderly classification between the elements? And the central element of this chapter is the periodic table, right, guys? So, just a second. Excuse me. So, the need to classify elements was felt in the 17th century, but only 31 elements were known at that time. By the mid of the 17th century, it doubled to 63. NCRT says at present 1114 elements are known, but uh, actually, if we uh, this is not the correct number. Actually, we have discovered all the 118 elements, but since NCRT is saying 114 elements have been discovered, so if a direct question is asked in JEE mains, then please follow NCRT, because they won't listen to your this thing. NCRT is the final proof they will accept. Okay, that is why I'm urging you to read NCRT. Okay, we'll move forward. The genesis of periodic classification, and there are some historical efforts which were made to classify elements. So the first was the Dobernier's triads. So we were at Dobernier's triads. So what are triads? Triads had an atomic weight about halfway between the atomic weights of the other two. So the middle element was really interesting. Then came Newland and he gave the law of octaves. He said that every eighth element has similar property. Okay. But it was true only for elements up to calcium. So they have given you a table of Dobernier's triads and a table of Newland's octave. You can go through them. Then working independently, there was a scientist named Lothar Meyer. He observed a change in the length of that repeating pattern. He observed a change in that pattern. So he said it's not a octave law or something, but the pattern is changing. And he arranged elements on the basis of that changing pattern, and he had developed a table that closely resembles the modern periodic table. But the scientist who's credited for the creation of the modern periodic table is Dmitry Mendeleev. And today we are almost studying Mendeleev's periodic table. That was the historic effort. So Mendeleev's periodic table he did some predictions. Okay, these are some important questions. So he predicted, he left he left gap under aluminum and a gap under silicon and called these undiscovered elements Eka aluminum and Eka silicon. They usually ask this. So gallium and germanium were not discovered at that time, but he predicted their properties. Okay, so this is Mendeleev's periodic table. You can go through it in your NCRT. There's nothing to be remembered here. Then comes the modern periodic table. It was after Henry Moseley observed regularities in the characteristic X-ray spectrum of elements. He plotted frequency versus atomic number. So Mendeleev was, what was the difference between these two? The difference is Mendeleev's was based on atomic weight, but the modern is based on atomic number. Atomic weight means proton plus neutron, but atomic number means only proton. So there's a difference between two. And Lothar Meyer gave us the a little bit modification in Mendeleev's law, almost the same, but it gave us the modern periodic table and the modern periodic law. So Mendeleev's law was changed, and the physical and chemical properties of elements are periodic functions of their atomic numbers. This was adopted as the periodic law. So the periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium, like actinium and protoactinium, are also found in pitchblende and ore of aluminium. This line is really important, the line which I just read, because many a times they ask direct questions from this line. So you should know what this line means. I'll explain it to you. There are a few elements in this line. Okay. Firstly, this line, before this line, it says that only naturally occurring 94 elements the law was given for. Okay. After 94, there are no naturally occurring elements. All of them are synthesized. So we cannot say that unlike the previous statements like 114 elements discovered and all, here you need to remember 94 are not discovered. They are naturally occurring elements. Here they say neptunium and plutonium, like actinium and protoactinium. All four of these are elements. Okay. And these are found in pitchblende and ore of uranium. This whole thing is about naturally occurring and synthetic. Although after uranium, there is no naturally occurring element, but some degree of neptunium, plutonium, actinium, and protoactinium are found in pitchblende, that is an ore of uranium. Okay. So basically, these four elements, although they occur after, they are after the atomic number 94, but they do occur in the ore of uranium. So you cannot call them artificial or synthesized elements. But there is no clear-cut division anyway. Someday we might discover an ore of your atomic number 105 or 106 also. We don't know. Chemistry is evolving every day. Next, we will move to the long form of periodic table, how it is arranged. So there are horizontal rows, which are called series, and the vertical columns, group. Okay, series or periods and groups. So periods are vertical. The horizontal rows are called series and the vertical columns are called groups. Then the vertical columns, which are called groups or families, they share some common characteristics. Okay. Pardon me for a second. We have covered periods and groups. Let's see nomenclature of elements with atomic number more than 100. Although questions are now not asked in this, but you just need to remember this one table for answering all those questions. So 0 stands for nil, 1 un, bi, tri, quad, pent, hex, sep, oct, n. So basically what you need to remember is 9 is called n here. Rest are easy to remember. Giving an example, suppose you have to name number 108. So you will name it at 1 stands for un, 0 stands for nil, 8 stands for oct, and last may you have to put ear. So un, nil, octium, right? The symbol will be un, nil, octium, UNO. Right now, the official IUPAC name for this element is hassium. Why have we adopted this system? Because if more than one countries discover an element, they want to name it on their scientists. And usually this results in clashes. So IUPAC, till the time it is not resolved which country should get the naming rights of the element, IUPAC gives a temporary name, and this is how they do it. Right. Next, electronic configuration. No need to discuss anything here. I will just tell you the relationship of this electronic configuration and periods. Okay. So the instead of just, I'll just give you what is there in the paragraph. Principal quantum number is n. N is the outermost shell, and this corresponds to the period number where that element will be found or will is present. Suppose you take sodium. So sodium, you write the electronic configuration 1s2, 2s2, 2p. I'm really sorry. It is 1s2, 2s1. So see, outermost shell is 2. N is equal to 2 for sodium. And we also know that sodium is in the second period of the periodic table. You can confirm it from here. See, sodium is in the second period. Then the new element gets a oh, did I just name lithium instead of sodium? Oh guys, I just named lithium instead of sodium. Forgive me. So yeah, it was lithium which we were talking about. So yeah, it is in the second period. That is the relationship of n with your period. Let's read about transition metal. Okay, this starts from scandium, which is Z is equal to 21. Electronic configuration of scandium is given. 3d orbitals are filled till zinc. Fourth period ends at krypton. They have given a transition series. Transition series starts from the, so transition series starts from, it is present after every, it is present in the fourth period, fifth period, sixth period, seventh period, and eighth period. Oh, there is no eighth period. It is present till fourth to seventh. And inner transition or F block elements, transition are D block element. Inner transition are F block element. They are present from fifth, sixth, and seventh periods. So yeah, they are present in these three periods. The fifth and sixth, the fifth one are called lanthanoids, sixth ones are called actinoids. Seventh ones, so yeah, seventh one, it is actinoid series. Then group wise electronic configuration. See, the outermost electronic configuration of a group same. That is characteristic. And they are categorized as S, P, D, F block based on the where the last electron is getting filled. So in an S block element, X block group, the last electron will enter the outermost S orbital. Similarly, in an D block group, the last electron enters in the outermost D orbital. Examples are, these are the examples of S block elements. Look at the outermost electronic configuration. It is NS1. So S block elements, here they are S block elements, P block elements, we have the D block elements and F block elements. Hydrogen is placed separately. Anything you need to remember in S block elements? I think you need to remember that they lose the outermost electron readily to form +1 or +2 ions. And they are highly reactive and never found in pure state. Okay. Then P block elements, group 13 to 18. And together with S block elements, they are called representative elements or main group elements. This is an important point. Sometimes they ask you some questions like this, conventional questions. Okay. Then valence shell configuration for noble gases they have given. And preceding the noble gases, they have halogens. Oxygen family is called chalcogens. Then nicogens are there. Before nicogens, you have the carbon family. Okay. D block elements. Okay. P block elements are usually non-metallic. Okay. And the non-metallic character increases as we move from left to right across a period, and the metallic character increases as we go down the group. We will discuss all of these in a while. Let's cover D block elements. These are the transition elements as we were talking about, group 3 to 12. So basically 1 to S block, okay, 3 to 12, D block, 13 to 18, P block. Very easy. I know you know all of this, but I'm just revising this for you. So the last electron enters the n-1 d electron, d orbital, okay, except for palladium where the electronic configuration is 4d10 5s0. Here the exception is there is no electron in outermost s orbital. Palladium is an exception. They show various oxidation states, they show paramagnetism, they are used as catalyst. Then one exception or one important thing, zinc, cadmium, mercury, which have the electronic configuration of full D orbitals, they do not show most of the property of transition elements. So transition elements are only from, they are accepted, like they are exempted from being called transition elements. So transition elements are from group 3 to 11, but D block is from 3 to 12. Okay, group 12 is not a transition element group. Then come the inner transition. Nothing much to be remembered about them. They are not of much use to us. Just remember the till what atomic numbers they extend. So lanthanides, they extend from Z is equal to 58, cerium to lutetium, Z is equal to 71. Then come the actinides, Z is equal to 90, thallium, till lawrencium, Z is equal to 103. Their outermost electronic configuration is n-2, F, n-1d, and ns2. These two series are called inner transition elements or F block elements. Then again, see, the elements after uranium are called trans-uranium elements, and they are usually synthetic. We just discovered, we just discussed this earlier. Coming to metals, non-metals, and metalloids. So we have divided elements into SPDF blocks, but there is one more division, which is metals, non-metals, and metalloids. So metals and non-metals, see, metals comprise of more than 78% of all elements. Okay, they are solids at room temperature. Mercury, gallium, cesium are a bit exceptions. They have high melting and boiling points. they are conductors of heat and electricity, they are malleable, ductile. This is all about metals. Let us go to non-metals. Non-metals are located on the top right hand side of the periodic table. Then in a horizontal row, the property of elements change from metallic on the left to non-metallic on the right. I'll give you a small solid hint here a bit later, okay, about how to identify. Then non-metals are solids or gases at room temperature, low melting and boiling points, poor conductors of heat and electricity, brittle, neither malleable nor ductile, and elements become more metallic as we go down the group. We'll cover that. So what are metalloid? Okay, metalloids show properties that are characteristic of both metals and non-metals, and they are called metalloids. Okay, the elements silicon, germanium, arsenic, antimony, and tellurium. So this is important. You need to remember which are known as metalloids. Only these elements are called metalloids. According to NCERT, do not follow any other book. This is what you need to follow. So I am repeatedly telling you, please don't stop reading NCERT for any kind of exam. And I hope you will take my advice seriously, because I have given JEE main and I know how much NCERT is helpful in answering the questions. They really ask direct questions from NCERT like this. They will give you, they know what you're being taught in different coaching or different other material, other books, but they set their questions based on NCERT to eliminate candidates. Don't get eliminated. Please read NCERT, follow NCERT from its core. If they ask you any question like which of the following is not a metalloid? Silicon, germanium, arsenic, and one more element which you have read in your some material as a metalloid, then you'll get confused. But if you know what NCERT considers as metalloid, you will never be confused. You will know that yes, if NCERT says that only these many are metalloids, then only these many are metalloids, because we all follow NCERT in making questions and answering them. So this is a really good take home point, and this point is really important that you read NCERT, especially in this chapter. I think a question might come from this metalloids. So we have done this metals, non-metals, and metalloids. Now let's see what are the trends in properties of elements. So what is trend? Trend is basically, you define trend as kind of what? How do you define trend? Trend is a sequence of pattern seen in any property. Suppose I take a property called height of students in my classroom, and I observe that not every student is very tall and not every student is very short, so everyone is medium heighted. So there is a trend that all the students of my classroom are of medium height. Understand what a trend is? Similarly, if we define some properties for our elements and we see how these properties are changing from one element to another, we can call it a trend, call that pattern a trend, right? And it's not really difficult to guess the trend if we know concepts. So we'll see trends in physical properties first. And the first trend is atomic radius. Very well, you can imagine, as NCERT says, size of atom as it is really small, but you know that, okay, it defines two kinds of radius, covalent radius and metallic radius. Okay. But usually we call it atomic radius. Now, the trends are obvious. Okay. Atomic size generally decreases across a period. Okay. For the elements of the second period, it is because outer electrons are in the same valence shell and effective nuclear charge increases as the atomic number increases, resulting in increased attraction of electrons. Within a family or group, the atomic radius increases regularly with atomic number. Okay. Usually for alkali metals and halogens, the descent in groups, the principal quantum number increases. The electrons are further from nucleus, so they are more in size. Note that the atomic radii of noble gases are not considered here. So because we cannot calculate their covalent or metallic radius because they don't form any bond. Okay. So see how the atomic radii is decreasing and how it is increasing in a group, how it is decreasing in a period. So you go from left to right, it will decrease. And you go from top to bottom, it will increase. This is the general trend. Ionic radius, this is where you get a lot of questions. So the one thing you need to remember is what is the ionic radius of isoelectronic species. So look at these four elements, they are isoelectronic. Always cations will be smaller than anions if they are isoelectronic. Why? Because they have equal number of electrons. Cation mean that they have lost electrons to come to that equal number of electrons, which means their protons are more. Okay, so they will get contracted. But anion means it has gained extra electrons to reach the state. So these extra electrons will be loosely held, so the atom size will increase. So comes the charge also. Here you can easily guess that Mg plus 2 having the most charge and it is a cation, it will be smallest, followed by sodium ion, then fluoride ion, last में oxide ion. This is the trend of the size. Similarly, here they have given the size. See, the largest species will be magnesium, smallest is Al plus 3. How? Ions, cations will always be smaller than their neutral parent atoms. So Al plus 3 is the smallest. Mg plus 2 follows it. And between Mg and Al, which will be larger? Of course, Mg will be larger because it lies to the left. So yeah, Mg is the largest, Al plus 3 is the smallest. Second trend is ionization enthalpy. So we have discussed atomic radius, ionic radius. Okay. Now let us see what ionization enthalpy trend is. Ionization enthalpy is the tendency of an element to lose electron. Okay. Energy required to remove an electron from isolated gaseous element from its ground state. This is the enthalpy of ionization. And the trends are that noble gases have the highest ionization energy, alkali metals have the lowest ionization energy, and the trends are kind of irregular after period number 2. Okay. See, period number 2, you have a peak at beryllium, you have a peak at nitrogen. Why? Why are these two? And of course, noble gases too, they are at peak. Why these two are giving a peak? Because beryllium is 2s2, fully filled. Nitrogen is 2p3, half filled. This both of them are symmetrical. Even neon is fully filled, 2p6. So see, a fully filled, half filled have symmetry. And symmetric means they are stable. So to remove electron from their shells, it will be difficult. So they are usually more than the corresponding element. That is the trend of ionization enthalpy across a group. It will keep on decreasing because atomic size decreases. So it is easier to pull out an electron. All right. Then we come to electron gain enthalpy. So how do you define electron gain enthalpy? Electron gain enthalpy is not the energy this required, it's the energy released. Okay, it's not energy that you give, but energy that is released from an isolated gaseous atom when it acquires an electron. So when you acquire an electron is roaming freely in space, and you acquire it means you bind it to the nucleus. So the potential energy of electron decreases. That will result in release in some kind of energy. This release in energy is called electron gain enthalpy. It is represented by this equation here. And depending upon the element, the process of adding electron could be endothermic or exothermic. See, IE is always endothermic. Okay, you remove the electron from the outermost shell, it is from a neutral atom. From a neutral atom, IE is always endothermic. But electron gain enthalpy can be endo or exothermic. I will just give you some examples where it is. See, exothermic, so every like generally it is exothermic, but I will give examples where it is endothermic. Consider the previous examples of beryllium, nitrogen, and neon. This is fully filled, this is half filled, this is fully filled. So if I want to add electron into each of these, will they want to gain an electron? They are fully filled. Okay. They are fully filled, but they are fully filled, and I will tell you one thing about them, that a fully filled and half filled is really stable. Okay. They don't want to lose this stability. There are numerous reasons for why they are so stable. We'll not go into that, but just remember, symmetry is what nature loves. They are symmetrical, they are symmetrically filled, gives them immense stability. And if you want to add an electron and make it unsymmetrical, because see, this is a half filled p orbital of nitrogen. You give it an electron, it turns into something like this. Where is the fucking symmetry here? Pardon my language. Where is the symmetry here? There is no symmetry here. The symmetry is gone. Earlier, it was completely symmetrical. So yeah, this is totally unacceptable. They will resist. So to add electron, you will have to put in extra energy. So electron gain enthalpy will be endothermic. So you won't get any additional energy release, but you will have to give energy. Okay. Look at the electron gain enthalpy of all the noble gases. It is so much. What do you say? It is endothermic, positive. Look at the electron gain enthalpy of group 17 and group 16. Usually they accept electrons. Why? Why do they accept electrons? See, oxygen needs 2 electrons to go to noble gas configuration. Okay. Similarly, your chlorine or any halogen needs 1 electron to go to a noble gas configuration. You give them electron, they're hungry for electron to achieve this noble gas configuration. Otherwise, if they have to achieve noble gas configuration, they had to lose some 6 electrons. So it is better to gain 2 rather than losing 6, right? They want to take the easy way. See, nature is very, it wants convenience. Okay. Everything, whenever you think of a problem, whenever you try to find a solution, think of the most convenient way. That is the way which nature is going to follow. Here also, the most convenient way is to lose, instead of losing, to gain 2 electron or 1 electron. So let's see. We'll see the trends in electron gain enthalpy. Group 17 elements have a very high negative electron gain enthalpies because they can attain stable noble gas configuration by picking up an electron. Other hand, noble gases have large positive electron gain enthalpy because electron has to enter the next higher principal quantum number, leading to a very unstable electronic configuration. Now, electron gain enthalpies have a large negative values towards the upper right end of the periodic table, preceding the noble gases. Now, the variation of electron gain enthalpies is less systematic than for ionization enthalpy. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. Okay. Down the group, because the size increases and added electron would be further from the nucleus, so the electron gain enthalpy, it becomes less negative. So it basically decreases down the group. This is acceptable because it will be further from the nucleus and it will lead to release of less energy. So if you tell me If I ask you oxygen and sulfur, which has the tendency to attract more electron? Definitely oxygen. So that you'll come to see in the next section. Why oxygen? See, oxygen tends to gain electron more than sulfur. That means oxygen is more electronegative. That is our next and maybe the last trend. What is electronegativity? It is a qualitative measure. It is not quantitative. Actually, we do like assign values to the elements for electronegativity, but it is a qualitative measure to attract shared electrons to itself. Okay, it is not a measurable quantity. We just attract a numerical value. For example, there are scales: Pauling scale, Mulliken-Gibbs scale, Allred-Rorschach scale. Now, the Pauling scale is widely used, and here an arbitrary value of 4 is assigned to fluorine, and because fluorine is the most electronegative element out there, right? Moving on, electronegativity, the trends are, see, electronegativity is not constant also. It varies depending on the element to which it is bound. Though it is not a measurable quantity, it provides a mean of predicting the nature of force that holds a pair of atoms together. Then electronegativity generally increases across a period and decreases down a group. How do you explain these trends? Basis of the previous trends. Okay, you can relate it to atomic radii, which tend to decrease from left to right, but increase down each group. See, it is all basis of how big an atom is or how small an atom is. Everything depends on that. Okay, if an atom is very big, then removing electron is easy. See, it's big, so removing is easy. Putting is easy, but less energy is released, and En is low because nucleus is very far from the periphery. If an atom is small, removing is difficult. Putting is easy and energy is more released. En is also high because nucleus is very close to the periphery and it can attract the shared pair of electron towards itself. Now, this is an important picture. You should take a screenshot of this. Like, this explains all the trends which we have so far covered. And if possible, you take a screenshot and try to remember using these arrows. The non-metallic character increases from bottom left to top right. The top right elements are really non-metallic. Metallic character follows the opposite trend. Ionization enthalpy increases from left to right. Electron gain enthalpy increases from left to right. Both of them increase from bottom to top, or they decrease from top to bottom. The thing about the peculiar thing here is atomic radius and electronegativity. Radius increases from top to bottom, but it decreases from left to right. Electronegativity, opposite trend. It decreases from top to bottom and increases from left to right. These are all the trends explained in a single picture. Now, electronegativity values, you should remember at least Pauling scale values. It is really easy. For period 2, just start from 1. Okay, so we have covered most of the periodic trends. See, reactivity is the thing. They have given a lot on reactivity, but you don't need to remember that much. Just remember that if this is the periodic table, then the ones at the top left and right are most reactive. That is the thing you can remember. Either less ionization energy or high electron gain enthalpy, which means either they form cations easily or they form anions easily. Then they are highly reactive. That's what you should remember. Moving on to some previous year questions. Let me go. Identify elements X and Y using ionization energies. So for first element, first ionization energy is low. Second one is drastically high. So it should be an alkali metal. For the second one, first and second are usually like they're comparable. So it can be an alkaline earth metal. So here, do we find something? Yeah, we have X is sodium, Y is magnesium. Next, characteristic of elements X, Y, Z are, oh, okay, it's based on the previous question only. So X and Y are metalloids. Where is X, Y, Z here? There is no X, Y, Z. So we'll skip this question. Then the next question is absolute value of electron gain enthalpy of halogen. Electron gain enthalpy, it decreases from top to bottom. Fluorine will have the highest electron gain enthalpy, followed by chlorine, bromine, and iodine. Then, which of the following compound cannot act as Lewis base? Lewis base is what? Donating lone pair, which cannot donate lone pair. NF3, it can donate lone pair. PCl5, it has a lone pair, it can donate. See, if PCl5, okay, if PCl5 donates a lone pair, SF4 can donate, ClF3 can. See, if PCl5 donates a lone pair, it will be, it'll get crazy and it'll have to, already it is having some 5 bonds. It'll have to make one more bond, which is not possible. It cannot accommodate 10 electrons. So it won't be donating electrons. The set of elements that differ in mutual relationship from the other set. Lithium, magnesium, S block elements, boron, silicon, P block, beryllium, aluminium. This is different. This is one is S, one is P. Rest other are same block elements. Then ionic radius of sodium is 1.02 angstrom. Ionic radius of magnesium and aluminium are. So sodium ion, magnesium ion, aluminium ion. Aluminium ion will be the least. Of course, both of them will be less than 1.02, but aluminium ion will be least. So I think second option is the most correct. Last question says, first ionization energy of magnesium is smaller as compared to elements X and Y, but higher than Z. Then X, Y, Z can be. Magnesium ionization energy is smaller than X and Y. So X could be argon. Definitely it could be argon or neon. It is smaller than Z. It's higher than Z. So Z could be sodium. So yeah, we get shortlisted from option 2 and 3. It cannot be lithium because lithium having a smaller ionization energy of than magnesium because it is N is equal to 2. So yeah, we go with argon, chlorine, and sodium. Okay, guys, so we are done with this chapter right now. It's an easy chapter. Don't need to put much effort in this. Okay. All right. So all the best for your exams. Thank you very much.